today's talk is, as you can see, about the age of the universe. And it will be, in part, obviously, about how we determine the age of the universe, all the different methods we use, and the combination of them, and the final answer we get to. But I want you to realize it's also a story about how we do science, and how science changes, and in particularly how our thoughts, how our understanding of physics have changed over the last century, and even over the last 15 years or so. The whole idea about the age of the universe has been turned on its head. And it's interesting because even the idea that the universe has an age is a comparatively new concept. And it's one that wasn't around at the end of the 19th century. And all the developments that have happened since have both introduced and underpinned the science of cosmology, the idea that you can treat the universe as a whole and look at its change, its birth, its evolution, and again, how it changes with time. But I'm going to start a little bit closer to home, and in particular go back to the Earth. And trying to understand the age of the Earth, because before you begin wondering about whether the universe has an age, you still have the initial problem, well, does the Earth have an age? And this, again, was relatively late to be introduced into science. It was recognized by geologists when, in this 19th century, when you have the understanding of how sedimentary layers build up over millions of years, that the universe must have the Earth must have some kind of long time scale to allow these rocks to lay down, one layer on top of another. And the fact that embedded within these rocks were fossils of creatures that resembled nothing like today's creatures suggested that a huge amount of time had elapsed between these layers being trapping the bones of these creatures and the day. The only problem was that people could not agree how long a time would have elapsed between these fossils and today's organisms. In terms of actually understanding or trying to calculate the age of the Earth, one of the most famous attempts that was really embedded in physics came from Lord Kelvin. And he worked on the premise that the Earth formed as a completely molten object. And he calculated that if the Earth formed as a completely molten object, how long would it take to cool down to the current temperature in the sort of present outer layers of rock of the Earth? Just from this sort of cooling of a hot object. And what he calculated was that it would last less than 400 million years, which sounds a long time, but that meant the age of the Earth was less than was then being required for this new idea of evolutionary biology, of all these generations required through natural selection for species to change and develop. And so his timescale, even though it's less than 400 million years, was too short. Now, it's too short because at the time he didn't understand, or we didn't know that there were other processes that heat the Earth. There's convection that carries heat from around the core up to the mantle. There's process of radioactive decay that provides heat in the layers of the rock. So this was, again, a problem. The age of the Earth that you worked out from physics seemed to be wrong and at odds with what you understood about the layering of the rock. And the radioactive decay not only produced a method for, producing more energy within the layers of the rock, it also gave a very good way to actually date rocks within the Earth. And this change happened around the end of the 20th century, end of the 19th century, turn of the 20th century, with the idea about stable and unstable isotopes. So let me explain. If you have a chemical atom, you have an atom of a chemical, mostly they're stable. They have the right number of protons, obviously the right number of protons, so it would be a different element, but right number of neutrons within the nucleus. Every so often you get a version of the element that's exactly the same. It'll go through all the same chemical reactions, but it's too heavy. It's got the wrong number of neutrons. Now, some of these are stable, and some aren't. And the unstable ones will just then undergo spontaneous decay. Well, they'll spit out the extra bits. So maybe, as in this case, it's spitting out a helium nucleus. It's getting rid of some protons and some neutrons and changing the number available in its nucleus. Maybe a neutron will split into a proton and electron, spit out the electron, retain the proton. And by this process, one element will change to another. There's some energy given out with each of these decays as well. So this process takes it takes place at a certain rate, and that rate is not affected by things like temperature or pressure. All you need is time. And the time scales for this process to happen can vary between billions of years to fractions of seconds. And so if you've got kind of radioactive decays from an unstable nucleus to a stable version of a much either lighter version of the same element or a different element altogether, if that takes a long time, you can use that in terms of radiometric dating to age a sample of rock. So, for example, if you assume you start off with a certain percentage of a parent element, that's shown in the light blue here, and we talk in terms of half-lives. A half-life is how long in time it takes for half that sample to have undergone the radioactive decay. And you can see that after one half-life, half the material has decayed away into the stable product, which we call the daughter material. And after so many lifetimes, half-lives, you can work out the relative percentage of the decay product versus the original element. So if you have a sample of rock from the Earth, you can work out, by looking at the proportions of the daughter and parent, how long it will have taken to have got to that percentage. This is radiometric dating. It provides a way of very good way of dating the rock. Now, it didn't quite work that smoothly in practice at the beginning. It was very complicated because I'm describing it as a very simple process. When you look at elements that have the long half-lives, that have the half-lives of billions of years, like uranium and thorium, they don't just go A to B without passing go. If you want to get from 238 uranium down to stable lead down here, there's a whole chain of different reactions. And even though it was recognised that this was a good dating technique, you have the problem of actually identifying all these interim interactions and then determining their half-lives in the laboratory. And it's particularly difficult if they're of the order of 4.6 billion years or 75,000 years. And this understanding meant that radiometric dating was not very accurate to begin with, but the person who pioneered with, basically persevered with it, was Arthur Holmes, who by the 1920s was getting dates for samples within the Earth of suggesting the Earth was at least a few billion years old. And this was in good agreement with the idea of evolutionary biology and the geology. The trouble is, a lump of rock on Earth is not a pristine sample. The rocks and the material that make up the Earth get mixed up. We've got plate tectonics, we've got volcanoes, we've got convection. There are other better samples to do your radiometric dating on. And in particular, one that's not so far away, the Moon. And okay, we're skipping right through to modern times now, but when astronauts brought back samples of the Moon from the highlands, the very heavily cratered parts of the Moon, which are thought to be the oldest parts of the lunar surface, radiometric dating on those showed that the surface of the Moon, the oldest regions of the Moon, those rocks were 4.5 billion years old. And here, the Moon has not undergone all those geological processes, so it's a much better guideline for the age of the Moon and presumably the Earth. And of course, you don't just have to go to the Moon to get the samples. If you wait long enough, some come to you. And another case of radiometric dating is from meteorites. Meteorites that fall to Earth. And again, the American geochemist Claire Patterson pioneered this in the 1950s. And it's done to the current day, where you're looking at elements within meteorites, and they're very consistent results. It depends on the meteorite. Some are at 4.53, some are 4.58 billion years old. Some of them, interesting, even predate the Moon and the Earth. And so it seems that some of these meteorites contain material that was in the pre-nebula before it collapsed into planets. But it's giving us a good idea for the timescale of the nebula that then collapsed to form today's planets. So we have a good coherent idea for the age of the Earth, 4.5 billion years old. Of course, it's very difficult to carry on radiometric dating if you don't have the sample in front of you. There have been attempts to do dating looking at uranium lines on stars. This is very difficult. You need a bright star. You need a good signal to noise to get the exact proportions of the elements. It has been done quite recently, the last 10 years, for just more or less a handful of stars. And the dating results are not very precise, but the answers are something like 12.5 billion plus or minus 3 billion. Not very precise yet, but this is a growth area. As soon as we get better telescopes, better signal to noise, you will see radiometric dating of stars becoming to the foreground. But if you want something that's bigger and brighter, say an entire galaxy, you kind of have a problem because galaxies are not pristine samples. You've got stars changing, condensing from gas clouds. So you've got material that's being exchanged between gas clouds to stars, then back out into the gas clouds, and all getting mixed up. And also you've got supernova going off and introducing new elements into the mix the whole time. So these are not good samples. So radiometric dating is limited. However, there are stars nearer to home, and in particular, you have the sun. And again, once you've established that the Earth might have an age, the obvious next question is to say, well, does the sun have an age? And understanding that, again, is not trivial because it's tied into what powers the sun. And realization, certainly in 19th century scientists, that we really did not know what powered the sun. And again, Lord Kelvin turned his thoughts to a possible energy supply for the sun, and working with the German von Helmholtz, they came up with this idea that the sun shines because it shrinks, basically. You have a large body, and the outer layers squeeze the inner layers, and you've got this process of gravitational compression, which heats up the inner layers of the star. Now, that's good, it provides heat, but if you calculate it from the size of the sun, it would only keep the sun shining for a few tens of millions of years. That's completely out, even with the age of the Earth as we knew it at the time. So even if you add in radioactive decay, this is not a good process to keep the sun shining. It can't be chemical burning because that's not an efficient process. You would use up the fuel supply or all the available matter in the sun, again, within a very short time. A new kind of process was needed to provide the energy of the sun. And the understanding of that only came in the early 20th century with this wonderful equation, E equals mc squared. Energy and matter are equivalent. So a tiny bit of mass can be converted to, well, any mass can be converted to an equivalent amount of energy. The nice thing about this is it's incredibly efficient. You can see this, so if this is the energy you get from this mass, this letter C is the speed of light, which is an enormous number. So a tiny, tiny bit of mass will produce an enormous amount of energy because you've got the speed of light squared involved in this equation. And this obviously was determined by Einstein, and it was Sir Arthur Eddington, here seen chatting to Einstein outside the back door of my department in Cambridge in 1930. I have to put that in. But he used these ideas and he worked out that the temperatures and pressures at the heart of the sun were sufficient that you could start undergoing reactions where hydrogen nuclei fused to form helium, release some mass, or some mass is liberated in the process, gets converted to energy, and you can then power the sun by this very efficient means. And the great thing about this is, I mean, obviously there's a lot passes in the interim about our understanding about these fusion processes at the core of the sun, but nonetheless, you can compare the luminosity output for the sun to the amount of material that's in the sun and how much is being converted from hydrogen to helium, and you can establish a very good date for the age of the sun of about 5 billion years old. And what's more, you can look at how much fuel is left at the right temperature and pressure in the heart of the sun and project that it's got a potential lifetime of another 10 billion years. So the star itself can be very long-lived. And obviously that's not one of the original stars right from the beginning of the universe. So the numbers are going up. So we've got a good age for the sun. And good reassurance is going to keep shining for quite a while. It's about 5 billion years, and after that you have the solar nebula forms with the meteorites condensed from that, just about sort of over 4.5 billion years, and then the planets and the moons come along about 4.5 billion years ago. So this is great. You have an idea of a finite Earth, the Earth having an age. You have an idea of stars being born and dying and having lives. But there's still another big step to comprehend that the universe can have an age. And a lot of our problem about this stems back right from the time of when Newton was developing his ideas of gravity. Great. Explain everything about the universe apart from one very simple fundamental observation, which is that when you look up at the universe, it's not all one big blob. Gravity is a pull. It's an attractive force. The fact that you look at stars and you see matter distributed into, nebulae and stars all over the place led Newton to infer that it has to be an eternal universe. It has to be an infinite universe, because there's only one way to stop gravity pulling everything together, which is if there's more stuff the other side of the stars and you have all the gravitational forces balance out. And this goes on ad infinitum. And so you have this fundamental concept of an infinite universe, one that's static and unchanging and eternal. And this mindset persisted for several centuries. And even when Einstein came along at the beginning of the 20th century, he completely overturned our view of gravity. No longer Newton's ideas of some invisible force acting at a distance. Instead, the idea that if you plonk a mass in the middle of space and time, it curves the space. And gravity is how objects move within that distorted, that curved space created by a mass. And also how light travels within bent space. Even though he revolutionized this idea of gravity, this picture of gravity, he couldn't get away from the same problem that Newton had. The space and the stars within, it's all distributed matter. It's not all one big lump. And his way of getting around it was to introduce the cosmological constant. Big name. It's effectively like a fudge factor. All it's saying is that gravity behaves in a different way on the larger scales. This is the only way he could get to keep the universe up and suspended in place, saying that on big enough scales, maybe there was like an anti-gravity that kicks in and keeps things from all falling together into one big blob. So this is Einstein's cosmological constant, and he's put it in there to keep the universe static and unchanging. And really, there was no reason why he wouldn't do anything different. This was the pervading idea at the time. Others used Einstein's equations. For example, there was the Russian meteorologist Alexander Friedman. He played with this value of the cosmological constant in Einstein's equations, and he found by varying the strength of it, you could get a universe that did change and move with time. And that introduces an idea of a universe that maybe evolves, that maybe grow from a young universe to the present-day universe. And then Georges Lemaitre, a Belgian priest, developed the idea even further. And if you really reduce the value of the cosmological constant, you could take this concept and say, well, okay, if the universe changes and evolves, and there was a baby universe and there's today's universe, maybe if you go back in time far enough, you have a beginning point, a creation point to the universe, what he termed the primeval atom, what we'd now regard as the Big Bang. And he introduced this idea of there was being a starting point to the universe. Now, they both independently came up with these ideas, which were rejected by the scientific establishment at the time, including Einstein. And the idea of the universe having a finite age really came not from the theorists, these guys doing all the equations and the thought about how gravity works, but from the observers. And this is where people like Edwin Hubble, very famous American astronomer, come into the mix. Now, Hubble was already famous, so we're talking about now early 1920s. He had access to one of the biggest telescopes in America, really cutting-edge technology. He had already established a name for himself by establishing that these little spiral nebulae, these little spiral clouds in space, were actually galaxies at much farther distance beyond our own. Here's his plate of our nearest neighbour, the Andromeda Galaxy. There's a star here. He's marked it as a variable. And he was able to work out the distance to this galaxy because this is a certain type of variable star that Henrietta Leavitt had shown. If you plot time against the brightness of the star, and this is Hubble's diagram for this variable, the time taken to go from one peak to another peak, because it undergoes this regular variability in its brightness, depends on how bright the star is. Really, its intrinsic brightness. So if you know how bright it should be here, so this is the luminosity you get from one peak to another, that's correlated to how bright the star really is. You compare it to the flux you observe, they're related by the inverse square law, 4 pi d squared, where d is the distance to the variable star. He did this. He showed that the Andromeda galaxy lay outside the size of our galaxy, and therefore established the idea that our galaxy was just one of, many island universes, as they called them. Okay, so he'd already done that. His next stroke was to combine these distances with the velocities of the galaxies. And we knew the velocities of the galaxies well. The problem had been working out how to determine how far away something was, and that's why that waited to the 1920s when this discovery about these variable stars had been made. Actually working out how fast galaxies were moving had been shown by Vesto Slipher in 1917, and you get this just from the redshift of the lines that's related to the relative velocity of motion of the galaxies with respect to you, similar to the Doppler effect. So Slipher had already shown that nearly all galaxies are receding. They're moving away from us. This is a big problem in a static, unchanging universe. You might expect some to be coming towards you, some to be going away, not all of them to be running away from us. But what Hubble showed, or his plot showed, and what he's really famous for, is this relationship between the distances and the velocities of these galaxies. And here's his plot. He shows there's a linear relation between the two. Distance along here measured in these wonderful esoteric units of parsecs. 1 parsec is 3.26 light years. Okay? Let's just make sure none of you follow what I'm talking about. I'm going to talk about really astronomical units against the velocity, the relative velocity of the galaxies. And here's a note to all future students. If you're going to have a world-breaking plot, make sure you get the units right on the y-axis. That's actually velocity. So it's a bit of a scrappy plot, but what you can see is that not only are nearly all the galaxies moving away from us, they've got a redshift, but the amount of redshift depends on how far away they are from us. So a galaxy that's twice as far away is moving twice as fast. This is Hubble's original plot. Now, of course, we extend this out to much further, more distant galaxies. Here's an updated plot. And Hubble's plot would basically be 2 megaparsec. It would just be that tiny corner. And you have this linear relationship out to enormous distances. And this plot is known as Hubble's law, and it's the signature of the expansion of the universe. And in particular, this slope of the plot is known as Hubble's constant. And that's giving us the rate of expansion of the universe. Now, it may be obvious to you why this one plot tells you that the universe is not static and is expanding. Just in case it isn't, let me just demonstrate. So if you're here, and there's a distant galaxy, obviously picture not to scale, right? But this galaxy is yay far away from us. Now, if we wait long enough, the space between us and that galaxy, maybe we wait long enough for that space to double, then the galaxy has moved yay far in that time. Now imagine another galaxy that's twice as far away. In the same amount of time as it's taken for this galaxy to move there and for this space to double in size, this space also doubles in size. So you have this space doubling, you have this space doubling, and that galaxy ends up moving over here. It's moved twice as far in the same time. It's moving twice as fast. Another galaxy 3 times away would have gone through 3 doublings of the space. It would have moved 3 times further away. It would have moved 3 times faster. So the idea that the further the galaxy, the faster it moves, is the just direct consequence of the expansion of space. And here I want to be clear that I'm talking about space expanding and it's carrying the galaxies along for the ride. It's not galaxies moving through space, but they're pinned to the space and it's the space that is expanding. So the universe is expanding. That means it's smaller in the past, smaller last week than it is today, smaller 100 years ago than it is today. You wind the equations back sufficiently far in time, you could go back to the idea that it was all compressed and so small that everything was compressed to a single point. And this is your singularity that is the start of the universe, the thing that Fred Hoyle later coined as the Big Bang. And so now you have the concept of a finite time. You have a beginning of the universe. You might have a way of reckoning on how long ago that was. And this expansion of the universe gives you a way to estimate that to a very simple approximation, which is that if you see a galaxy, you've got a galaxy over there, and it's a distance d away from you, and at the point you observe it, it's moving away from us relative to a sort of velocity v, if you know the velocity and the distance, you can work out how long it's taken travelling at that velocity to cross that distance. And therefore, it's taken a time of d divided by v to travel to have got to that separation away from us. Okay, so if we go back to the plot, Hubble's constant, remember, is the slope of this graph. It's the gradient. It's velocity over distance. Got to put a little bit of maths in here, okay? So I've just told you that the time taken to expand over there is d over v. So 1 over Hubble's constant gives you what's known as a Hubble time, which is basically the age of the universe. So you can do it for one individual galaxy. It's much better to do it for a full sample of galaxies and get the general relationship. And that's what you're doing by getting the Hubble's constant. And why? You read all these papers about the determination of the Hubble constant, how it underpins our understanding of the cosmos. This is why it gives us an age to the universe. Of course, it doesn't always work that beautifully in practice, and it really didn't for Hubble. With his original plot, he estimated an age of the universe which was 2 billion years old. This was then already less than Holmes had been establishing for the age of the Earth. So there was some difficulty about getting this idea originally accepted because of this mismatch. You know, the universe can't be younger than objects within it. But nonetheless, a lot of observational cosmology through the last century has been to determine a precise value of the rate of expansion of the universe, Hubble's constant, and therefore get the age of the universe. Of course, you can't look at these individual variable stars in nearby galaxies. It's easy from the ground, but if the ground-based telescopes, if you want to go to more distant galaxies and therefore sample more back in time, because remember, if you're looking at galaxies that are 1 billion light years away, you will see you're mapping out the expansion of the universe within that billion years. And the fact that that law is so, that Hubble law plot is so straight for galaxies out to 1 billion light years away means it's more or less unchanged in the last billion years. Obviously, you want to go further, you need more distant galaxies, and for that, you need something like the Hubble Space Telescope. And a lot of key projects using the Hubble Space Telescope was to determine the Hubble constant to as good a detail as you can. And looking at individual variable stars and distant galaxies, here's some data from the Hubble Space Telescope. If we just take that block there, you're looking at variability of these stars. The precision is amazing. So we'll come back to plotting out the Hubble constant in more detail soon. But I just want to say that, of course, this is ongoing, but there are other ways to guess the age of the universe that was also being undertaken during the 20th century. For example, a star, an early star like our sun, so one that was born a lot earlier, when it throws off its outer layers, as this one is doing, to have the center collapse down and form a white dwarf, something like this here. There's a white dwarf at the center, the outer envelope of the star expanding away. You could say that that white dwarf is just going to sit there and it's going to cool. And so if you go out looking for the coolest white dwarfs, they should be the oldest white dwarfs. And again, looking at what you'd expect, how you expect them to behave and what temperature they've reached now, you could get some lower limit to the age of the universe. So far, it's quite difficult to do because the coolest white dwarfs are going to be the faintest white dwarfs, the hardest ones to find. And there isn't any great discrepancy yet between that and cosmology. The big problem came from clusters of stars, globular clusters. These are if you look at the elements within the stars, we think these all formed at a very early stage of the universe. They're not very chemically enriched. All the stars, we think, formed from the same gas cloud. They all formed at the same time, they've all formed from the same composition, and they're all the same distance from us. So if you can age the stars in an old cluster, again, that gives you a lower limit to the age of the universe because you've got something in the universe. It's got to be younger than the universe itself. And how you do this is how bright a star is depends on its mass. More massive stars burn brighter, they burn hotter. So you look at the luminosities of the stars and you can work out their masses. And then mass determines the age of a star. A very hot star, a very massive star, only lives a few tens of millions of years. If you've got, in this sort of sequence when they're doing nuclear fusion, hydrogen to helium to progressively heavier elements, a less massive star lives for a lot longer. And so with a cluster of stars like this, you determine basically what are the faintest stars that are still undergoing ordinary nuclear fusion. You can then work out their mass and their age. And a huge problem was that even as the observations of the Hubble constant from distant galaxies were getting refined and getting to very good values, even like about 1958, there was a huge mismatch between what they were saying and the dates from the ages from the clusters, which were about 25 billion years. It could be a factor of 2. They're now reconciled, but only through a lot of development, say in the 1980s, about understanding the stellar structure of stars in more detail, and also radical redetermination of the distances to globular clusters, meaning that actually they turned out to be a bit nearer than we thought, the stars brighter, and therefore the stars in the cluster younger. But again, you've got all these checks going on. And by the time the official announcement at the turn of the 20th to 21st century, the rate of expansion of the universe was determined from the Hubble constant of 73 kilometers per second per megaparsec. Now, it's esoteric units again. What this means is for every megaparsec, so that's every about 3.3 million light years you go further out in space, that bit of space is receding away 73 times faster than here. It gives you the stretching. Or if you like, every sort of million years, a bit of space will expand by 0.007% or something. It just gives you the rate of stretching. But by the time we got this result from the Hubble constant, things had moved on about our understanding about space and time. And in particular, you realised that the Hubble constant itself was not enough to establish the age of the universe. You needed to take into account the fact that the energy and matter within the universe would affect this expansion. You had to make a correction. And this involved summing up how much stuff was in the universe. So just to remind you, if you have mass and through E equals mc squared, you can also include radiation, you can include energy. Stuff in the universe, whether it's mass or energy, bends space around it. It curves space. And the wonderful phrase here from John Wheeler is matter tells space how to curve and space tells matter how to move. This is how Einstein's picture of gravity works. So if you have a lot of stuff, your space is very curved. Now, this works locally, whether you've got a galaxy or you've got a whole cluster of galaxies. It also works on the grander scales. So if you could sum up a long part of the universe and work out the overall curvature, you can work out how much stuff there is in the universe. And you get various extremes. Now, what we're used to is flat geometry. All this means is if you sum up the interior angles of a triangle, they add up to 180. If you have two parallel light beams going off, they stay parallel. Where if you have not very much stuff in the universe, perhaps you have an opposite effect where it's called an open universe. There isn't so much curvature because there isn't so much stuff in the universe, there isn't so much gravity. And here you have it's analogous to a saddle-shaped geometry. Your parallel beams go off and they actually diverge. They don't stay parallel. That's one extreme. The other extreme is you've got a very dense universe, lots of stuff in it, a lot of gravity, a lot of curvature. And here, again, it's analogous perhaps to the surface of a sphere. Your parallel beams will converge eventually as they travel across the universe. So if you like, these are the three extremes. And if you could measure the overall curvature of as much of the universe as you can work out how much stuff is in it. It's also got consequences for what might happen to the whole universe. So if you've got a very heavy universe, very dense universe, there's a lot of gravity. The universe starts expanding away, and then gravity pulls it back in, and you have this recollapsing in the future. Your time is going from present to the future, and then this is the past. So a dense universe pulls itself back in after that initial expansion. A very lightweight universe, the open universe, there isn't enough gravity to pull it back together, and it carries on expanding away. And the borderline between these two is known as the critical universe. So this is, if you like, a density required. How much stuff in the universe is required on the boundary between these two events. And this critical density is not very much. It's something like 6 hydrogen atoms per cubic meter. So you don't need a very dense universe to have this critical universe. And again, if you've heard of this parameter omega, all it is how dense the universe is compared to that 6 atoms per cubic centimetre. This is called the critical density, and if it's greater than the critical density, that's when there's a lot of stuff. The universe is closed. If it's much more lightweight, if it's less dense, you've got the open universe that carries on expanding. In terms of my diagrams, this is your omega-1, this is your dense universe, a much larger omega, and except I've got these the wrong way around. Sorry, very embarrassing. But you get the idea. You've got the much denser universe. So, how do you measure the curvature of the universe? Well, that effect that it has on parallel beams of light is really what we use. And you want those parallel beams of light to sample as much of the universe as you can. So you're summing up the curvature of the universe over as long a distance as possible, as much of the universe as you can. And we have the ideal background light, the cosmic microwave background. It's not uniform, it's mottled. I mean, this is a temperature map. This is the earliest light of the universe. It's got literally hot spots that are slightly denser than the surroundings. Now, we know enough about plasmas, ionized gases, at the kind of temperatures, pressures, the kind of physical properties that we see in the cosmic microwave band here. We know what we should expect about the size of those blotches within the microwave background. We can compare it to what we see, means how have those light rays been diverted through space. So if they're really yay big, if it's a flat universe, we see them subtending the right size. If it's an open universe, the beams have diverged, and so they appear smaller. If the beams have converged, we're fooled into thinking the blotches are much larger than they should think, and so we'd expect to see different things to what we actually see. The long and short of the story is, it's this one that wins. They're the right size. We live in a critical universe. It's this one. We live in a flat universe, and there's a problem with this. It's very clear from these blotches, the size of these fluctuations, that we live in this universe, but there isn't enough stuff in the universe. If you added up all the matter, whether it's light-emitting matter, dark matter, you add up all the radiation energy, it only comes to a quarter of that critical density. Okay? So this was the problem. You have a flat universe, but not enough stuff in the universe to make it flat. So another way you can test this is by just trying to sum up the amount of matter in the universe, maybe look at clusters of galaxies. Those of you who came to my talk on clusters of galaxies know that you can sum up all the light in a cluster. So a cluster is just gathering of hundreds of thousands of galaxies. They're nice samples of the universe. They're nice little closed samples. You can pick one here, you can pick one several billion years away further. You can just sample the properties of the universe through time. And you can add up how much light and how much matter, or how much matter is that's what we call baryonic, the ordinary matter that's giving off light. You can compare it to the total mass of the cluster, and you can find out what proportion of the whole cluster is the ordinary matter. We call this the baryonic fraction. How much the ordinary matter compared to the total matter. And the thing is, we don't expect there to be any conversion. We expect this to be uniform throughout space. You can't change ordinary matter to dark matter. They're very different beasties. So if you sample this fraction in all these other galaxies, you get a good idea of this ratio. The ratio is about 12%. This means that you can work out, again, how much matter there is in the universe. If this ratio between ordinary and dark matter is 12%, well, we know how much ordinary matter was created in the Big Bang. That's another story that I'll come to another year. That's primordial nucleosynthesis. You can't do it in less than an hour, probably. But anyway, you've got this. You can work out how much ordinary mass there is. You know this ratio, and therefore you can extrapolate to how much of the rest of the mass there is. And again, there isn't enough. With all these clusters, you get the systematic result that you've only got 25% of. We only observe 25% of the mass we need. So you have a big problem. You've got a flat universe. We're trying to sum up how much matter there's in it, and we're getting discrepant results. So one thing you can do is then go back to your Hubble law plot and say, OK, if the universe, let's go and see what point the universe starts slowing down. Maybe that will give us another way of estimating how much mass there is in the universe. When does gravity start pulling everything back? You need to go back further out to more distant galaxies, and then you can map out the expansion of the universe to much more distant times. Now, you can no longer use those variable stars, even with the Hubble Space Telescope. They're too faint. You can't resolve them in an individual galaxy. The breakthrough in the 1990s was the idea to use supernovae, and not just any supernovae, supernovae type 1a. And these happen from a very particular circumstance. If you have a sun-like star, when it reaches the end of its life, it expands to a red giant, it chucks off its outer layers, just as I was talking earlier, the centre shrinks down to a white dwarf. Well and good. But imagine that star's part of a binary. When its companion swells up to be a red dwarf, it can then accumulate mass. And you get to the point where if it accumulates enough mass, it'll then get to the point where it can no longer hold itself up as a white dwarf. Gravity overcomes it, and it undergoes a supernova explosion. And this happens at a very definite trigger when the mass is about 1.4 times the mass of our sun. And this is your type 1 supernova. It's a very particular type of supernova compared to the more ordinary ones where it's the death of massive stars. And the nice thing about these is you get this huge burst of light. It can be seen in its host galaxy halfway across the universe. It can outshine its host galaxy, so you can see them a lot further away. The other thing, of course, is that it happens at an exact same trigger point in all these objects. It's a very predictable outburst, a very regulated explosion. And so all these are kind of very reproducible outbursts. And indeed, observationally, okay, just showing you, here's before, here's during outbursts. See how bright some of these supernovae are. You can see them billions of years across the universe, up to sort of 5-6 billion light years away. Oh, it's a bit bright. But there's a certain uniformity to the explosions, and you can characterize basically that brighter supernova take longer to fade away. You can normalize all of these, but the effective thing is by seeing how bright the supernova is, you can work out how bright the supernova is by mapping how slowly its brightness decays with time. If you know how bright it should be, you compare how bright it is, you can work out the distance to the supernova and the galaxy they live in. So this is a great way of pushing the Hubble law plot out to further distances. So if this is the nearby universe, and confusingly we've now swapped axes, I apologise for that. Velocity's down here and distance is out. It's a linear plot, same idea. If you now go out to where we'd see the distance to the galaxies of the supernova in, kind of got a problem that the supernovae distances all sit off this line. The line starts to curve. This means that those very distant supernovae are fainter than we expect, fainter than they should be, and that's because they're further away. These objects are further away than they should be. Something has happened to the expansion of the universe. We're here. Here's our distant galaxy, again, not to scale. Supernova goes off, the light travelling towards us, and at that point, the relative velocity between us and the distant galaxy, say, is v. That means that we can expect that in the time that elapses, the time it takes for that light to reach us, the galaxy's continued moving at v, and we've separated off to a certain distance. We expect where the galaxy's got to. What we're seeing instead is that light is given off the supernova, it's receding at v. We'd expect it to be the AFAR, but in fact, it's a way lot further, which means the expansion is speeded up in between. The expansion's got faster. It's further away than it should have been. And so this was established by two independent teams looking at supernovae. The universe is not undergoing constant expansion. This expansion has accelerated. It's getting faster. And this has happened during the last half of the universe's history, within the last 6 billion years. And for this, certainly Perlmutter and Schmidt led the two teams doing these independent supernovae surveys. For this discovery, they shared the Nobel Prize. So if the expansion of the universe is sped up, okay, that means that the universe is younger than we thought. And it means there's something going on beyond just what happens to gravity and how gravity pulls things about. There's more physics involved. So you've got two things to reconcile. You've got the fact the universe is expanding faster than we expected, okay? And not just that, you've got the fact that if you sum up all the matter in the universe, it's only 27% of what we need to provide the geometry of the universe we see. And the way that we can counter both of those with one stroke is to say there's something else. we're missing 3/4 of the mass energy density of the universe. So we suppose that the missing 3/4 is something called, it's going to be energy, because we don't see it in terms of mass anywhere. It's going to be some kind of energy. It's going to be 3/4 of the universe. And it's not going to interact with light in any way or anything like that. It's not detected directly, only by the effect it has on other objects within the universe and the expansion of the universe. And this is why we've got dark energy. Now, don't get hung up on the name. Dark just means we can't observe it, and energy because it's energy rather than mass. We could just as well call it magic pushy stuff, and it would be just as accurate, but this is a bit more dignified. The dark energy is what has been discovered in the last 15 years, and it can reconcile everything about the cosmology we don't understand. And it means there's this extra component to the universe. So in particular, you have this extra 3/4, which in itself is providing this push and accelerated expansion of the universe. So in terms of not understanding much of the universe, this is what we see. Okay? We infer that that sits on dark matter, which doesn't interact with light in any way, but we can infer it's there from gravity, the attractive force of gravity. That's another 20%. We're now invoking another 75%, which makes the universe flat and conforms with everything, all the observations that we see, but we don't know the form of the dark energy. But nonetheless, we think it's there. And what's more exciting is that we think it's an inherent property of space. Again, very different idea. We're used to gravity. The amount of gravity you have depends on how much mass there is in something. Imagine instead you have some property, some force, that depends on how much space there is. It's actually interlinked with space. So the more space you have, the stronger the dark energy. So if you have a small universe, stuff is close together, gravity dominates, it pulls stuff together. And you've just got gravity dominating the universe, you've got the initial expansion and the way gravity works within that. As soon as the expansion is such that you start getting larger and larger volumes of space between objects, the dark energy gets stronger. And when it gets stronger, it acts as a kind of anti-gravity, providing a push that starts pushing the universe apart faster and faster. And so we live in an accelerating universe. So it's none of the above. It's not you closed, it's not you expanding. It is kind of changing halfway through the universe and getting faster and faster. So we have a very different kind of universe from the one that we're expecting. And certainly the teams were not expecting to find this in the 1990s. So we have this wonderful thing called dark energy. How do we know what it is? Well, there are probably as many different ideas about dark energy as there are astronomers, but I'm trying to encapsulate it down to 3 basic ideas. And the first one of these, which appeals to a lot of people because you don't need to invoke, perhaps, you're going back to tried and trusted physics, you're not invoking terribly new realms of physics, is to go back and revisit Einstein's idea of the cosmological constant. Instead of it being in error, because he removed it because he didn't need a static universe anymore after the expansion of the universe had been proven. But imagine it really isn't there. Maybe that's telling us that gravity behaves on a very different way, acts as a repulsive force on huge distances. Now, lots of people are playing with that idea. We've yet to get it to work precisely. You've got to change the equations and not violate all our observations for how gravity behaves. And that reconciliation means that if there is a cosmological constant, it's going to be very different from the one that Einstein envisaged. You're either going to have to change the equations or you're going to have to change the nature of space. And some people do that by invoking extra dimensions of space. So there's no easy answer within that, but it's still a very attractive option. Alternatively, you could apply to what we know about particle physics. Even empty space is not truly empty. You've got little pairs of particles and antiparticles winking in and out of existence, creating and destroying each other in fractions of a second. And every time they do this, they produce a little outward push. And if you have a large enough volume of empty space and all these little annihilations going on, well, then you maybe produce a big enough outwards pressure. This is known as the vacuum energy of space. There's still a mismatch. We can't get it to work. You can predict what you'd expect from the particle physics, compare it to what we observe in terms of the expansion of the universe, and our understanding of particle physics overpredicts this vacuum energy by a factor of 10 to the 120. So it's a major mismatch. We need, this again, this is rooted in our current understanding of physics. Obviously, and it could yet be reconciled with a better understanding of particle physics. So this is astroparticle physics, where astronomy and particle physics are providing constraints on each other, which I find a fascinating field. And then, of course, you always have the option of a completely new force field. This is called it's very often called quintessence. The idea of a fifth essence, beyond earth, air, fire, and water, which again tells you that it's not a much better name than dark energy. But again, these tend to be rooted in the idea that there's another force field that perhaps only becomes important at certain times in the universe or certain kind of physical situations within the universe. And the appeal of this is this could be related to that very intense burst of inflation that happened after the Big Bang that provided the initial expansion of the universe. Maybe now we're going through another period like that. It's just a much milder period of inflation. So these, if you like, are the three main options. And the question is, how do you tell which is right? And that's the next set of observations cosmologists want to do. They all predict different things about how the dark energy increases. So if you double space, does the strength of the dark energy double, or does it triple, or does it quadruple? And the next thing we have to measure, therefore, is the rate of change of the acceleration, which is known as the jerk. And yes, I've heard all the jokes about finding jerks in astronomy. But this is the rate of change of the acceleration of the expansion of the universe. And for that, the next generation of cosmology projects are going to be looking even further out into space. And as I say, these different theories predict different things about the jerk. They also predict different things about the future of our universe. We know the big crunch is out. Again, time, scale of the universe, we are here. But say the dark energy is constant and it just grows linearly with space, then the universe is going to get very old and cold, and that's going to be known as the big chill. If the dark energy gets stronger and stronger, this acceleration is itself going to accelerate, and we end up with something called the Big Rip, which is a very catastrophic and highly speculative end to the universe. So, there is incentive not just to find out, what on earth this dark energy is, but also what it might tell us about our future and the future of the universe. But I've kind of got away from the topic, which was the age of the universe. This is projecting into the future. We do have a good understanding of the age of the universe. Once you correct for the amount of energy and matter within the universe, including this dark energy, you can account for the curvature of space, you can then get a very good result for the age of the universe. And the current best estimate, and it's not an estimate, okay, it's a very good calculation, and this is from a paper by Bennett et al. Just last month, so it's hot off the press. The answer is 13.772 plus minus 0.06 billion years. And that's with quite a high degree of accuracy, where the errors are kind of due to systematics in the data rather than the actual, our understanding itself. So with that comforting thought, we now know the age of the universe, but just think how far we've come in that last century, even the concept of the universe having an age, and all the physics we've had to learn to establish that age. And for me, it's really exciting to think of all the physics we're going to discover with all the things that cosmology has overturned and demonstrated that we don't know about our universe and we've yet to refine. So my last slide, complete change of topic, but we meet again in a month's time, and we're going to go right from the very big to kind of much more kind of planet size, and I'm going to be talking about exoplanets and how to find them. Thank you.